The scientific revolution starts now.
This is the Science Joy Podcast.
Let us see in the dark.
Something that we're really interested in is how to shift the landscape of people's thought. How do you get people to think about scientific questions in a different way? And you're kind of at the forefront of that because I can't think of anybody who's more credentialed than you. And yet you've been having a hard time bringing these ideas to the world to some degree. And so hopefully we can talk about that and kind of get a lay of the land from your perspective.
Well, the last time I got in this situation was when we were doing the VLSI stuff. And I had started the little project here at Caltech and was teaching a class of a few students how to design these chips. And we had made our own homebrew design tools and were able to generate really good artwork and get it plotted by a plotting device and make masks from it. And meanwhile, the people in the industry were using Rubylith and drawing things by hand and cutting them into the Rubylith by hand. And it was a nightmare. And I couldn't get them to see that what I was doing would be valuable to them. But I was teaching the students that. And then the students would get through and get a degree and go off and go someplace, and they saw the people there doing things by hand, and they said, hey, there's a better way of doing this. And once in a while, one of them would get a chance to try, and then that company would start doing it. And it turned out if it weren't for the students out there actually doing it in companies, it probably wouldn't have become the standard for a very long time. But just pushing it and pushing the notion of increasing density was okay because the physics was all right, because we had done the physical measurements. So we knew we weren't going to get into trouble for another 4 orders of magnitude. But it was a hard sell. You just can't believe. And this is something that would benefit everyone. We weren't trying to be secret about it or anything, but it was a very hard sell.
What year was this approximately?
In the early 70s.
So you're saying that in the early 70s, people were still making lithography masks by hand?
They're making masks by hand, yeah. They would draw them on Mylar. First of all, they'd start and they'd draw a logic diagram, and then they would hand translate that to a transistor diagram. And then somebody would look at the transistor diagram and do a layout on a piece of Mylar. And then they put the Mylar on a light table. I have pictures of this in my Kyoto talk, pictures of them doing this. Absolutely, they'd put the Mylar on a light table that had this thing called a coordinatograph. And it had a very precise way you could move the knife blade. And you could only move the knife blade in X or in Y. So you would set the X on one of the grid lines on the Mylar, and then you would move it in Y to get one edge of the stripe, and then you'd move it over one little grid on the Mylar, and then you'd move it again by hand down. And they did this for the whole chip, and it was nuts. And they had people full time just doing all this hand layout and all this cutting of the Rubylith. In fact, the famous picture of Bob Noyce and Gordon Moore and Andy Grove was sitting looking at very proudly at this piece of ruby lith, all done by hand.
Wow.
It was completely crazy.
It reminds me of the first printing presses, or the typesetters every morning for the newspaper, going and changing the letters out.
Absolutely. And they were
Wild.
doing it, and I couldn't convince them. It was unbelievable.
Why couldn't what could you not convince them of?
They it just they looked and nodded and smiled and kept doing it their own way, and it was and finally some of the students would go out and do it in other companies, and then eventually one of the companies that made mask making equipment made a pattern generator, so you didn't have to use Gerber plots like I was doing. And then that got to be mainstream. But it was 10 years of, us being the only ones doing it that way. And then the students graduated, and then they went out, and then it became a more competitive way to do designs. It would save at least a year, maybe two, in the design process. So it was nuts. But it's a hard sell. Anything that's different from what everybody is doing is a really hard sell.
I mean, at least with technology, eventually it proves itself. But with theoretical ideas in science, how do you can, a really bad idea in science, not really bad, but one that is less effective than another, might persist sometimes for 1,000 years because it doesn't really affect people's lives, especially with astronomy, astrophysics, cosmology, electrodynamics, let's say at the theoretical fundamental level.
Well, I've got the experiment coming up that I'm actually going to do in in my way of doing gravitation. Well, let's start with what GR does. GR has a field equation, and the field equation is what you use to calculate anything. And then there's an auxiliary condition that you just stipulate, and that is what the velocity of light does, not in the field equation anywhere. So there's a number of things you can do. Einstein, in fact, did several things in the history of developing GR. And in 1911, he recognized that there's a variable speed of light. And of course, you see that directly in the Shapiro Delay when you send a radar off to Mars or Venus and get a reflection. When that path goes near the sun, the delay of the reflection goes way up. There's a great big peak in it. So it's a direct observation of the slowing of the speed of light with the gravitational potential. That experiment, they didn't have radar back when Einstein was doing that, and let alone radar that you could see a reflection from Mars. And Shapiro figured that out. Now you can get that result with GR by making a change of coordinates, and you change into the coordinate system of the observer, which has a variable gravitational potential, and you get that the length of the measuring rod gets shorter when you go by the sun, when you go in a place of lower gravitational potential. GR shortens the measuring rod, and it slows the clock. So you get an effect from the clock slowing down proportional to the gravitational potential, and the measuring rod slowing down by that gravitational potential. So the actual measured speed of light slows down by 2 times. And that's the famous 2 times that GR predicts over Newtonian prediction if light was a little bullet. That was done in, the 1919 eclipse, and was what made Einstein famous. It was seen as the biggest thing that anybody had ever done. Well, I think Einstein would have gone back to his 1911 theory if he'd known about the Shapiro Delay. Because Einstein was very much rooted in experimental findings. And in fact, in his 1911 paper, he ends it saying, independent of any theory, it is of interest to know if with present instruments we can detect the effect of gravitation on the propagation of light. That's a wonderful open question. I think if he had seen the Shapiro delay at that point, he would have said, okay, that means the assumption we make that's over and above the real, the root of GR is the field equation. But over and above that, this is an auxiliary assumption. It's not built into the calculations until you need the speed of light somewhere and you need the gravitational potential somewhere. So,
yeah, what do you think would have changed had he known that?
yeah, I think he would have pursued. Abraham was well along on a theory of light using a theory of gravitation using a variable speed of light, and I give a reference to that in the thing I have on the web. And he was ahead of Einstein for a while, and it was actually a very good scientific debate that was done on the pages of the journals, and it kept both of them energized in terms of what are the physical effects. Einstein kept saying, what's the physical effect you need to represent? And Abraham had a more mathematical approach. And then, of course, Einstein got more and more mathematical in the process of the debates with Abraham. So it was.
What was Abraham's physical interpretation?
Oh, he thought there was a variable speed of light, because if you assume that, you can make a very simple form, which is what I've done. But in addition, I work with the wave nature of matter, the quantum assumption instead of a classical assumption, and that gets you a lot further because you can build in special relativity without sacrificing the rest of it. It becomes an approximate theory then, but you can see there might be a way of making it exact. It turns out there are very few systems that push a theory anywhere near where the nonlinearities in general relativity come in, and there are actually some errors in my view errors in interpretation. They actually count the they actually count the gravitational field as having an energy of its own. If you work with potentials instead of fields, these questions don't come up like that. And you can do a much cleaner separation because energy comes from the potential times the amount of matter that's at that potential. So the energy is a very well-defined thing. Whereas in a straight field theory, there's all these arguments about how much energy is in the field and how much is in the matter. And that's a complicated question. But anyway, how would you decide a question like this? I have an approach where the speed of light has two factors. It has the slowing of clocks, which happen at one factor of the gravitational potential. And that's been observed directly. It's been made possible by the wonderful high, extraordinary resolution clocks that the people in Colorado and the people in Germany are building. And you can see the change in the rate of clocks with gravitational potential now down to millimeters. Some of the recent work at Colorado. So that's all good. You know what that factor is, but that factor has been measured on lasers which have standing waves of light between two mirrors. And it's been measured on other clocks like atomic clocks. But the speed of light that's measured in the Shapiro delay is a different kind of, it's what we call a traveling wave. You send a code out from your radar and it goes out and it's little pulses. And it hits Mars and turns around and comes back. It's little pulses. Well, the pulses travel with the group velocity, which is a derivative of, let's see, how do I want to say that? It's a derivative of the frequency with respect to the propagation vector. And the speed of a standing wave is the frequency divided by the propagation vector. So they're different if there's a medium in which the speed of light changes. Then it would be called dispersive. And you would get a difference between the speed of a pulse traveling one way and a standing wave, which is just sitting there oscillating. Well, it just turns out that in the last 20 years or so, both of the groups that I mentioned have developed these things called optical frequency combs, C-O-M-B. And the reason they call that is if you take a pulse and put it between two mirrors and have it bang, 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 back and forth, what you get is in the frequency domain, that's a bunch of frequency lines equally spaced at the round trip time of the pulse. And you can, in one optical cavity, you can get a standing wave, and then you can modulate it by a little envelope, which then bangs back and forth. And both things can happen in the same cavity at the same time. And what that gives you is, when you look at the frequency with a spectrum analyzer, you get the bang, bang, bang frequency, but you also get the standing wave frequency. And there's a beat note between the two at the optical frequency. And because they've made the cavities so good and the nonlinearities so good, they can actually make the spectrum such that the low part is at some frequency and the high part is twice that at optical frequencies. Fantastic. And then you can make a beat note between the lowest one and the 2 times that. And you should get the low one again, and you don't. And that difference is the difference between the speed of a pulse and the speed of a standing wave. So it's a direct measurement of the difference between the traveling wave speed of light and the standing wave's speed of light.
Hey guys, our show is entirely crowdfunded. We need your help to continue to make these shows twice a week. It takes a lot of time to put these together, to reach out, to edit these things, to release them. It's actually an unbelievable amount of work, and we need your support to continue to make it happen. Jump over to patreon.com, and for a couple bucks a month, you can actually get involved in the planning and direction of this. We have weekly meetups with our patrons. It's an incredible community, and you can help us out just by coming over. You can also share this podcast with somebody, leave a comment, make sure you're subscribed if you're not already. These are really important factors when it comes to guests deciding whether or not to do the show. Otherwise, enjoy our conversation with Carver Mead. We'll see you next time.
Hold on 1 second. I want to pause here and make sure, because that's kind of complex. Shilo, I feel like I didn't totally follow.
I'm thinking about it in terms of musical synthesis.
Yeah.
Because I'm thinking about these harmonic relationships between the two frequencies.
Can you explain?
And you're talking about creating this chirp, like this, you're putting an envelope. Maybe you can explain the envelope process to us a little bit better for how you generate the pulse signal.
So hold on, let's zoom out even a little bit farther than that, because you're talking about, so you have this mirrored cavity, and
it's a laser essentially.
But there's a laser that's shining into the mirrored cavity, right?
But a cavity is a laser, as far as I understand.
Well, not in this case, but that's why I didn't say it that way. But many lasers have a cavity like that. But the reason you don't want to use the laser for this measurement is the laser has stuff in it, and the stuff in it messes with the speed of light. So you want a pure vacuum cavity to do this experiment. The important thing here, let me get to the bottom line, and then we'll go back to the experiment again. Okay? Because I was right at why is this important? Well, in my theory of gravitation, the thing we call c, the speed of light, is the speed associated with a uniform gravitational potential. So it's the speed of a standing wave. Well, where's the factor of 2 that Einstein is so famous for? That factor of 2 comes from the fact that the photon, when it goes past the sun, it has momentum. And we know from gravity probe B, and it's also evident in Einstein's 1912 theory before GR, and it's evident in GR, that matter has a gravitational vector effect on other matter. If you have 2 masses and you accelerate one, it very slightly accelerates the other because there's a vector coupling. Well, photon has momentum, so it's going to have a vector coupling to the sun when it goes by. And if you just work it out, which is in the handout that you know about, it turns out that because it's going at the speed of light, that's a factor of 2 in the effect on light propagation. So a pulse is slowed down twice as much by gravitation as a standing wave is. Well, here we have an experiment which directly measures the difference between the speed of a standing wave and the speed of a traveling wave. So what we're going to do is build one of these, and I'll describe it more carefully in a minute. And I'll work with the guys in Colorado on this. There's a little company called Octave Photonics, which has incredibly talented people, and they've been able to make a nice portable one of these systems so we can put it in the back of a van and take it up on Pikes Peak and directly measure the difference between the speed of a traveling wave and the speed of a pulse. And I'll either be right or I'll be wrong.
Isn't the traveling wave the same as the pulse? Sorry, I got confused.
I'm sorry.
You said the difference between a traveling wave and a pulse, but isn't the traveling wave the pulse?
Standing wave and a pulse.
Oh, I'm sorry.
Oh, okay,
Yes.
just check.
Thank you. It directly measures the difference between a standing wave velocity and the speed of a pulse, the traveling wave velocity. Thank you. So let's go back to the experiment again. We have some method of making a light field in a cavity. We do it by putting it in from the outside. And we make that field have a standing wave and a pulse that goes back and forth, both. Turns out it's very easy to do that if you're one of the people that have been making these frequency combs. Typically, an easy way to do it is to start with just a plain old laser that has a steady wave coming out of it. And you let that fill up the cavity with a standing wave because it just goes in and bounces back and forth until it's nice and steady. And then you modulate the light coming in with a little pulse so that it has a bright spot. And then that pulse goes into the cavity and bangs back and forth. And there's lots of tricks in getting the pulse to be only a few cycles wide at 10 to the 14 cycles per second. But because the beat note between these two frequencies is a part in 10 to the 12th or 10 to the 13th for this one, the change in,
And that's in the time domain? 10 to the
yeah, let me just do it. Speed of light, standing wave light, changes by 1 part in 10 to the 12th per meter height. Sorry.
So we're talking wavelength now.
Yeah.
Gotcha.
The speed of standing wave light measured very well. And it changes 1 part in 10 to the 16th per meter of height in the Earth's gravitational field. So you get a part in 10 to the 14th per 100 meters height.
Mm-hmm.
Well, the light is 2 times 10 to the 14 per second. That's the standard wavelength that's used for communication optics. And so you can get all of the optical things you need at that frequency. So that's what we use. Then,
So let me see if I understand this so far. So you have this cavity and you put light into the cavity that stabilizes so that it's a standing wave which doesn't appear to be moving, right? So you basically
nice
have
and
this
steady.
stable, and at that point the standing wave is just the fact that the amount of time that it takes for it to cross the cavity and to come back, it means that it's perfectly in sync, and so you get your wavelength is the same. There's no phasing.
Yeah, think of it as like an instrument string, where you have a string on a guitar or a piano, and if you pluck it in the middle, it will be fixed at the ends, but it'll oscillate and it'll have one your half wavelength across the length of the string. But if you pluck it very near the end, it'll set up a little pulse that goes across and bangs back and forth, and you can hear that. So that's the kind of thing that you can visualize happening in the cavity.
And
It's like a phasing overtone, right?
yeah, I'm kind of
Yes.
imagining basically like a pulse of the modulated envelope pulse as traveling the same path. Like in my mind, I have this picture, and the picture is you have mirror, mirror, and then you have this perfect standing wave that's in between them. And then when you add the pulse, you have some kind of disturbance in that standing wave that travels at a speed that you can measure.
It's periodic, right? So it's going to go in and out of phase,
Yeah,
right?
Yeah,
because it's overlaid. It's basically overlaid on the standing wave.
yeah, that's
Okay.
a good way very good way of looking at it. Yes,
Okay.
it's like you have a standing wave on a if you pluck or drive a instrument, the string on an instrument, it will get to where it's vibrating at harmonics of its length. And you can get it to, if you have a little something that vibrates it at those frequencies, you can get resonances where there's a very large number of half wavelengths in the length of the string. So that's what's true of a cavity. You have a cavity, the wavelength is, say, a micron, and the cavity is like several centimeters, but let's say it was a centimeter. So that would be 10 to the 4 wavelengths in a 10 to the 2 times 10 to the 4 wavelengths in a centimeter cavity.
And so the size of the cavity is tuned to match the wavelength of the light that's being put in so that it's a direct multiple so that it can bounce perfectly.
Yeah. Well, said the other way, what you do is you tune the light going in electronically to where it's exactly matched to the cavity, and the cavity is then the reference for the frequency of the light you put in. And you do that with a phase locking technique. It turns out you can do all of radio tricks today at optical frequencies. So they make a phase lock loop at optical frequencies. So much for quantizing the radiation field.
All right, so the standing wave makes sense to me, the height dependency of that, where there's more gravitational pressure at the lower altitudes, and so you're going to, I mean, ultimately light's generated by atoms, so you're putting a lot of pressure on the atoms. It makes sense that their vibration, their photo emissions.
Let's go back. Light isn't carried by atoms. Light is carried will be in a perfect vacuum, the most perfect vacuum we can make on Earth. And
well, the light has to come from atoms, right, and go to other atoms.
Oh yeah, but when it's in a cavity, and you're absolutely right, it has to bounce off atoms in the mirrors, and so its source is always atoms, of course, and that's why it appears to be quantized when people do measurements on it. But and the atoms in the mirrors do have dispersion. And it's been observed for a long time that there's this difference between the frequency of the traveling wave and the frequency of the standing wave. And it's always been blamed on the mirrors. But actually, it has a component, according to the way I do gravitation, it has a component that's due to the gravitational potential.
So can I just check something really quick? You're essentially comparing this. The standing wave tells us what light is doing at a baseline in the system itself. Say, in the experiments with the radio beams to Mars coming back, these are what light is doing at the sun, or where the gravitational potential is greatest. That's your baseline. But in this experiment, you're able to compare that baseline to the traveling velocity of packets of light that are going through that gravitational potential. So you can compare the travel versus the baseline. And you're saying that there's a difference.
Yes. And the important point is Shapiro had the whole mass of the sun to work with his radar experiment. And it was brilliant. That was in the late 60s, and it was fantastic insight that he had. That was the first time we could see directly, without any hocus pocus, that the speed of light depended on the gravitational potential in the frame of reference where we measure things. Now, you can always, Einstein and his co-workers and followers have elegant ways of transforming physics from one coordinate system to another. So you can express it in any coordinate system you want. They chose to express it in a coordinate system where the speed of light was constant, independent of the gravitational potential, because they thought it was good somehow. And I don't agree with that choice. I would rather express physics in the frame of reference where I do the measurement. Then it's evident. So anyway.
So what's the significance of the all right, so the background light, the light travel, the standing wave, what's the significance of that differing from the travel? Is that because it's interacting in the traveling wave is interacting dynamically with the gravitational field, whereas the standing wave is not? There's no change in its position?
Great question. We know that if you have electrons in a wire, they're standing waves. And the reason we know that is because there's no current in the wire. But if you put a current in the wire, those electrons have momentum, and that's coupled electromagnetically by this thing we call the magnetic field, or the magnetic interaction. Light has the same thing with the opposite sign, because like things attract in gravitation, and opposite things attract in electromagnetism. So the vector effect is the opposite in gravitation, but it's been observed. The first time it was directly observed was in Gravity Probe B. And instead of the press saying the first time we had seen directly the vector interaction of gravitation, they said, oh, we didn't learn anything because it agrees with Einstein's theory. That's part of the blindness of our age. It isn't the theory that tells the physics what to do. It's the physics that tells the theory what to do.
Can you elaborate on the experiment of Gravity Probe B?
Oh, yes. Gravity Probe B was a beautiful experiment done by the Stanford people. And what they did is they took a little spinning ball that they levitated, because if you're in space, nothing has any weight. So you can levitate it with just a very, very little bit of charge on little plates. You can push it back and forth, and you can keep the spinning ball away from the cavity that it's housed in perfectly. And you can do this in a very good vacuum. The only, just the leftover you have from the vacuum of space. So they did that. And if you think of it from the point of view of the little spinning ball, it's sitting there, it's a little gyroscope, it's sitting there, and its coordinate system, it's in free fall. So its coordinate system is as good as anybody else's free fall coordinate system. Well, what does it see? It sees the big Earth going around it and around it and around it. And the vector interaction is going to try to turn the little spinning ball, and that will make its direction of rotation shift a little bit. And they made this beautiful experiment, and they observed the shift just what you'd expect from the Earth going around. And it was a lovely thing. Very first experience we had. This is 2004 already. And before that, we had never observed directly the vector interaction due to gravitation. That was an amazing finding. We know that.
I'm sorry, go ahead.
We know that there's a vector interaction between anything with momentum and matter anywhere.
Yeah, that's what I was going to ask is what's the story with the momentum in the standing wave? Is it that the vector momentum on balance is canceled out because it's just traveling both ways essentially?
Exactly.
Got it.
Perfect. So it's like the wire, it has no net current. It has half of it going one way and half of it going the other way, but that makes a standing wave. And it has no net momentum, so it has no slowing due to the momentum coupling.
Check.
So let me see if I understand about Gravity Probe B. If you were to not have the ball spinning, would you see the same vector coupling?
Excellent question. It turns out you'd see half of it.
Interesting. Why half?
And you have to work it out. I do this in it's in a chapter of the thing that my class notes that I put on the web, and you can read about it there. There's a whole chapter on Gravity Probe B. That's actually how I got into thinking about gravitation, because it was such a gorgeous experiment. And to have it not understood at a physics level, but only understood at a mathematical level was a big disappointment for me, because nobody got it. What a fundamental finding it was.
Did you have a chance to talk with the people that were working on that project at the time?
Oh yeah, I talked to them. Of course, all they said was, well, it works according to general relativity. Yes, but you have to do a fancy coordinate transformation into a coordinate system where the presence of matter changes the units of measure. And you have to work in that system to get that answer. And it's a nightmare. They're very, very smart mathematical people that can do that. I can't do that. And So I asked myself the question, is there any way I could understand this experiment?
Nice.
Because I can't do that kind of math. I could probably learn how to go through the motions, but to believe that I hadn't missed something would be impossible. And in fact, there's been a lot of that with general relativity where people argue about whether it's a real effect or a coordinate effect or this or that. And I look at that, I couldn't live in that world. It isn't evident what the law is. And I need to live in a world where the law is evident, like Feynman said.
Hmm.
And so that's my reason for being here.
Well, it's fascinating how oftentimes in science you can propose a way of looking at something that turns out to be very accurate, but still incorrect. And I'm thinking of classical examples like the caloric theory of heat, right? Where you can model heat as a flowing fluid and the mathematics are sound, it does work out, but there's a less complicated way of looking at that turns out to be more physically accurate. And I think that it's very easy to get lost because something is very predictive and it works out. And even technologically, you can make heat engines, right? All the basic thermodynamics were developed using this technically incorrect theory of heat, but the mathematics was sound, it was predictive, and yet it is wrong. And that's a really troubling hurdle in the whole process, the scientific method, because it doesn't prepare us for the possibility that something could be predictive and incorrect.
There's a long history of that, as you know, and when Newton came up with his stuff, they were calculating orbits using epicycles, which is a way of doing an expansion. And they had got very good at it. And it was many years before Newton's theory could do predictions that were as good as the epicycles. So they kept saying, hey, our thing works. Well, but is that what the physics is doing? And that's a different question from whether you could get the answer by doing that mathematics.
And it seems like you need to develop really smart experiments to distinguish between the two at some point, right? I remember with the caloric theory of heat, they eventually realized that because it was an inexhaustible substance, it couldn't actually be a substance, right? They were boring out these cannons and they could just generate infinite quantities as long as they kept boring, right? And so this contradiction, it's kind of an accidental discovery in that case. Nobody designed that experiment, but in order to separate out these sort of effects, when you have equally predictive models, you have to really, really be clever about how you discern between the two, and it's not always obvious.
The history is full of exactly that kind of thing, where we have two examples here. There are more. What's amazing to me is that since the three theories that we rely on, electromagnetism, GR for gravitation, and quantum mechanics for atomic things, they were all done before any of these really precise experiments were conducted. And yet the results were not factored into the theories because the theories came first. And the theories came out of a very old mechanical science that had been well developed. So it was the science that people knew that then got extended into this new realms. And sometimes it works. And one of the things we've learned is that you can always elaborate things mathematically to where they work. And if you're on a track, it's easier to do that than it is to start over and say, hey, maybe we had the wrong idea. Like with the caloric thing, yeah, heat is it's a palpable thing. It's something you can imagine as a substance, and it kind of acts like that. And so it was hard to give up. You really had to think about things in a really new way, and that took a long time.
Yeah, it seems like it's still playing out with electricity to some extent. Like, electricity is also treated as this kind of magical fluid right now. And I wonder how that paradigm will evolve in the future.
Oh, it's an excellent question. We have the same problem with that. When quantum mechanics was being formed, they just assumed that it was the electricity that had been worked out by Maxwell and his followers. And it seemed to work. But then there was this problem when you had an atom and you had an electron around a proton in a hydrogen atom. And you could calculate the energy levels with the old original Schrodinger form, where the wave function was a physical thing in three-dimensional space. And so they calculated the lines and everything looked good. There was a reason that the transitions were quantized, because they had the stable states in the atoms and they had to go from one to the other. And that's a nice physically understandable process that Schrodinger worked out in great detail. But then if you tried to do the same thing with a helium atom, well, it's two electrons. What's the problem? Well, the problem was that the electromagnetic theory didn't work. So then you went back to the hydrogen atom and you realized that what the assumption had been was that this cloud of charge, which is the electron wave function, doesn't interact with itself. Well, what's that about? Has to interact with itself if it's electromagnetic. No, you just assume that electrons don't interact with themselves, but only with other electrons. Well, that's awkward. It turns out it's never been resolved. What happened instead is hydrogen found a math hack that he could put each electron in its own three-dimensional space. And then you could choose when you wanted them to interact and when you wanted them not to interact, and thereby satisfy Pauli's dictum that says electrons can't be in the same state. And we've been stuck with that 3n dimensional space ever since. So all these calculations have to be done in 3n dimensions. It gets exponential very, very worse than exponential very rapidly. Moore's law has not been able to keep up with it. So we're still making approximations to get the real energies in molecules and things. And nobody's gone back and said, electromagnetism at the level of the individual wave function doesn't work the way we thought. And we have to go figure out what's there. So this theory that we thought we had so beautifully worked out is actually rotten all the way down to the core. And we have to start over there and figure out really what the interaction between two charges in when they're both electrons. And what we find out looking at, for example, superconductors and how their energies depend upon the symmetry of their wave functions, you find out that the symmetry of the wave function affects what the electrical interaction is. So it's not just the charge density, it has the wave function in it. And nobody's gone back and figured that out. So we have to go back and figure that one out. So
how do you rally people to go back to these fundamental assumptions? It seems like a continually appearing demon in science. It's so difficult to muster efforts towards reassessing fundamental assumptions. What's the best strategy for that for young people coming up? I mean, how do you find time to go back and assess these basic foundational principles?
It's very difficult. That's a central point in our culture today. If you go into science, you get told to get good at these theories that are our current zeitgeist. And if you get good at that, you can pass the courses and you can get a degree and you can get a job. And if you don't get good at that, you can't do any of those things.
Yeah.
So guess what? It was just like the young people did in Hitler's Germany. You either became a Nazi or you got your head cut off. Well, you don't blame people for making the choices they do. So our current system digs the current trench deeper and makes it harder to get out of because people aren't prepared for looking at the direct observation of the physics. They say, oh, which equation do I solve to get that answer? That isn't the question. The question is, what conceptually is going on in this experiment that causes this behavior, which is different than the stated. I'll give you an example of that. The quantum mechanics, the way it's taught and the way it's said to be practiced, says that the transition, that makes the spectral line, we don't talk about that. We only talk about the probability of that. That's the party line. Well, if you can't talk about it, you can't talk about how sharp the spectral line is, because that has to do with how fast the transition in the atom is. Because if you make a very fast transition, then have a big broad spectral line. And if you make a slow transition, then it'll be a very sharp spectral line, and that's observed. And there's a lot known about it. Well, how do they calculate that? Well, they use this thing called Fermi's golden rule. And what that says is, I will consider the atom that's excited and wants to make a transition. I will consider it as coupled to all of the modes of the vacuum. And they're oscillating away, interacting with it. And then I will calculate the probability that the atom will still be in its excited state as a function of time, which you can do because it's a probability theory. But that's a question about, if I excite the atom, how long will it be in that state relative to being in some other state? That's a question about the individual atomic process. What they do is they calculate it as if it was an ensemble, and they say how long on average before the atom is no longer in its excited state. And then they apply that to the width of the spectral line, was a question about the individual atomic process. So the theory of quantum mechanics that's supposed to be so precise and so good, they don't follow the procedure that they teach the students to do. And then they teach them this cheat, which is a very effective way of calculating what happens. But they don't say that it's physical. They say it's all just probability. That's totally incommensurate with the postulates of the theory in the first place. So the theory inside itself is rotten. And it has to be, because otherwise it wouldn't predict the right width of the spectral lines. Predicts spectral lines, but it doesn't tell you how. So the theory in itself is rotten. It's not consistent with its own postulates of what it's calculating. This is the lengths you have to go to hang on to a thing that's just obviously not right.
Yeah, like what systematic changes, if you could rebuild the academy, if you were king of the world, how would you make room for challenges to fundamental assumptions? What would that look like?
Well, I'm doing my best. You people are doing your best. We now have technology for reaching young people that we never had before. They could go on the web and they can find a lot of really good material. They can also find a lot more real junk. I feel like it's our place in this society to point in directions that help them find where the future might be. We can't do it all, obviously. But in the past, one experiment has often turned the nature of scientific inquiry. People always point to the Michaelson-Morley experiment as being the reason we don't believe in an ether anymore. Actually, the facts are a little different than that, but that gave people something to hang on to go learn this new thing called relativity. And nowadays we have much better ways of thinking about relativity as applied to atoms and as applied to these vector couplings and all those things. But so the technology gives us a window onto physical reality that's vastly clearer than anything we had when these theories were cobbled together. So
I'm sorry.
We just need to use it.
Yeah, I mean, I can imagine like a course in first year of graduate school where you are forced to go and re-examine some foundational contradictions that might exist, like to seek them out and to actually identify where there are mismatches in our fundamental understanding so that you can apply that to whatever nuanced experimentation you're doing down the line. Because I think most students come up through the academy and aren't aware that there are foundational contradictions that everybody knows about, but aren't really examined, or they're not given the chance to really examine them. It's almost like you said, you get in and you're cranking because you have to get funding and you need to do something that's safe and builds upon what came before, and there's just no space for students to even learn about the ideas that are at the root of a lot of the problems today.
Well, I want to say that it feels like the real challenge isn't contradictions necessarily, because everything that we're talking about here isn't contradiction, it is a material interpretation of the phenomena. Because there is a fashionable quality to mathematics where, when I look through the history of physics for the last century or so, to me it seems like it became increasingly mathematical because math is hard, and it is a status symbol to be able to do exceptionally difficult mathematics. And you see even, there's this really famous interview with Feynman where somebody asks him to explain how magnets work. And he kind of laughs it off as this thing that's an absurd question to begin with, where the mathematics is enough, and to ask how the magnet works is kind of this absurd gotcha question. And
Actually,
so,
it's a very nice question, and it's easily answered conceptually,
okay, do you want
which
to
is
drop that?
different than answering it mathematically.
And to connect it to what Shiloh's saying, which is that, having a period of grad school where you go through and you look at fundamental mismatches. Beyond that, I would say not just to look at mismatches in our understanding of things, but to ask, what are the things to which we don't have a material explanation? Because right now, everything bottoms out at the quantum field, and the quantum field is a mathematical construction that it's math at the very bottom of everything. It's just moving vectors.
Yep.
Yeah, I would say relativity is equally dissatisfying because it's just telling you a statement of what everything looks like. It's not really telling you what is happening on a material basis. Right?
I would agree.
That's one of the things that I was faced with in doing a new approach to. It's actually not a really new approach. Abraham did something like it, but it didn't. It didn't quite get it, but made a valiant run at it. And that was 1911 when Einstein was still having a variable speed of light, and they were in that debate. But yes, in order to have young people aware that there are such things as concepts that have to be understood before you start writing equations. That's an idea that has gradually died out of science. And the way kids are taught now is if you want a physics course, well, it's this equation. And that doesn't cut it. So we have to start clear back with K-12, teaching people about momentum just like we used to. You get on your little trolley and you have to push yourself to get going. But once you're going, you go along pretty well. And people can understand that conceptually. They don't need an equation for that. The equation can come once you understand the concepts. So that for me is the thing that has suffered the most.
Something really strange happened in the late 1800s, this switch to relativism where previously it was assumed that there was a material mediator for light and gravity and that we needed to understand how that worked, but then people abandoned that idea. Was that just the Michelson-Morley experiment that caused people to turn away from this idea? Because it seems like that opened the doors for pure mathematics to run away with the entire industry.
It was certainly a central part of, and Einstein got a lot of resistance to special relativity for exactly that reason. And I think much of the resistance was not thought through, but some of it was thought through. And it's exactly on this point of, when you're on the train going past the train station and you see everybody as skinnier, then are they really physically skinnier? Or is that an artifact of the fact that you're using light to see them?
Mm-hmm.
And that question comes up in the context that I'm talking to you about. What is physically real? So the discipline that has not been applied to our present theory is that if you're going to say that clocks run slower, there has to be a physical mechanism for why the clocks run slower. You'll find a whole discussion of that in the student handout on the web. It's a discipline that I think is a necessary discipline in any science, that there needs to be a physical mechanism for the mathematics that you postulate. Now, that doesn't mean we're going to know all of them, but it tells us where to look. It suggests experiments like the one I explained to you that nobody thought of. So we need to get back to where we're teaching kids starting in first grade or kindergarten about concepts like inertia and the speed of light and things that kinetic and potential energy and what a potential is. The idea of a potential has been largely expunged from our modern physical theories because they have this story they tell about, well, there's something wrong with it because you can change it by a constant and it doesn't change, or by a gradient of something and it doesn't change the field, therefore it isn't right. Well, that's just wrong. It's the fact that it's the gradients, it's the derivatives of the potential, which you're calling the fields. And anytime you take derivatives of something and just work with those, you've lost the value of the constant integration that you would have to get back from your derivatives is gone. So the potentials are the fundamental quantities in physical law, not the fields. And the fields are those derivatives. And you've thrown away a level of abstraction when you don't work with potentials. That's been, that whole line of thought got started with electromagnetism because they wanted the ether to be a physical thing that light could propagate in. And if it was, well, then it was the E and the V were the twists and the stretches in the ether. And those were physical things. So in their effort to be physical, they were looking for an ether. And Michaelson and Morley couldn't find it. And there's a long story there, but setting that aside, it was the first time that special relativity got a hearing because people were arguing over it. And then the Michaelson-Morley experiment, whatever you think of it, gave people a hat to hang on. And they had a thing to grab onto. Before you jump over, there's something on the other side. And so that was something they could grab hold of. So that I think was the importance of that experiment.
Yeah, it's almost like Einstein came along and said, well, don't worry about finding the ether. We don't really need it to describe what's happening here. Whether it's there or not doesn't matter because we can describe it in this new way that doesn't necessitate that in our physical theories. But isn't that a little bit of a tragedy, though? Because it sidesteps the question of mediation rather than addressing it head on. And of course, that's just not a topic anyone's worked on for 100 years.
Yeah. And I'm sort of bringing it back to front and center with this new experiment. It is still, if you have the speed of light changing as it goes by a massive object, well, what is the gravitational potential acting on that changes the speed of light? How does that work? We don't know how that works. And we better be clear about the fact that we don't know. The biggest thing that has disappeared from scientific thought is the ability to identify what we don't know. And we pretend we know it because we've hacked up some math to give us some results that sort of work. And I think what we've proven is that we can always do that. You can always make math that if you find out you have to do more stuff, you make the math more complicated and you can get it to do that stuff. But the question that people are asking about the ether is just as alive today as it was then. And I'm going right into the middle of it. I don't have an answer. I don't know how gravitational potential from a matter here can affect the speed of light over here. I don't know how that works. Nobody knows how that works. Is it a question that makes sense? I don't know that.
What?
But we have to admit the things we don't know.
I would love, so we actually have been working on these material atomics explanations for various phenomena, and I would love to send you our video, because we have a vision of an explanation for gravity, that if your experiment shows the thing that it shows, that I think we could explain it.
I mean, for us, it's all about the structure of the atom itself and how the actual shell is organized. And so we made a little video. I think we should just send it to you later and just get your feedback, because Anastasia came up with an explanation for the Shapiro effect based on this radioelastic architecture. And it'd be interesting. I mean, we're not saying we're right, but it makes sense to me. It could at least be one explanation. And as we know, sometimes there's multiple explanations, and it really takes the test of time to show which one's right. So
this is exactly what needs to happen, is that the questions need to be asked, and it will become clear which ones we don't know and which ones we do. And then the ones we don't know, people will have ideas about, like your idea. I think it's wonderful. It opens up science to be science again instead of to be religion. And they're different things.
We have a list that you gave. You printed us out a list when we met you this winter of effects that needed attention. And I love that. And we have it on our wall still, actually. I actually meant to bring it in for this conversation, but it's pinned to our wall. And we have to make our way through that list eventually. I hope you have an even longer list that you are cultivating somewhere.
Well, it's on the very introductory part of the handout is my list of known experiments that change what we think about fundamental physical law. And so you can add that to your list. It's I forget. Do you want me to look it up? I might even be able to find it.
Sure, and I'll go grab the one that you gave us. Hold on.
Well, you can find it. It's within the first few pages, and it's a list with numbers, and it lists the experiment and what it showed us.
We'll put a link to the handout.
Mm-hmm.
Yeah, you have a link. I think we should go, but I'm kind of out of gas. But this has been great to talk with you, and I am glad to hear that you're asking those questions which you couldn't ask if you were in one of the establishment contexts. Right.
Yeah, we're lucky to be able to work on the outside, and I think more and more people are finding ways to do that. And so, yeah, thank you so much for coming by. It's always a pleasure speaking with you. I know we could talk to you for hours and hours and hours, but this has been a real gem of an hour.
This is great. I love talking to you too, and you have such a great approach to everything, and lots of success with that.
Thank you, Carver. You as well.
All right. Have a great rest of your day.